Welcome to the deep dive. We're here to cut through the noise, really distill complex topics into the vital insights you need, so you can be genuinely well informed, without feeling totally overwhelmed. Today, we're plunging into a topic that, well, it affects all of our health, our future: antibacterials. Think of it like this ongoing, invisible war against microscopic invaders. Our mission: to understand the arsenal we use. We're going to try and unravel the science, maybe debunk some common myths, and hopefully arm you with a clear understanding of what these powerful substances are, how they work, and why they're just so central to global health discussions right now.
Absolutely. And we've pulled together a really fantastic collection of sources for this deep dive. It covers everything from the fundamental biology of bacteria right up to the broader, pretty pressing issues of antibiotic resistance.
Okay.
So by the end of our conversation, you'll definitely have a much clearer grasp of not just how these treatments function, but crucially, what their impact means for you and, well, for all of us in public health.
Okay, let's try and unpack this unseen battlefield then. When we talk about fighting infections, we're fundamentally talking about confronting specific disease-producing organisms. So to really get a handle on our weapons, first we need to understand the enemy, right? What are these microscopic adversaries we're mostly targeting with antibacterials? We're talking bacteria. And they're these distinct life forms known as prokaryotes.
Indeed. And that term prokaryote itself is actually a key insight. Unlike our own cells, which are, complex, they have a nucleus. Bacteria are simpler. Much simpler. They're single-celled organisms, no membrane-bound nucleus, none of the other specialized bits we have. And this fundamental structural difference is actually one reason we can target them with drugs without, hopefully, harming our own cells quite as much. And when you look at them, they have these distinct shapes, really crucial for identification. You've got bacilli, those are elongated, sort of like tiny rods. And then there are cocci, which are spherical, perfect little spheres. And even within cocci, you get variations. Staphylococci, they clump together almost like grapes.
Oh, okay.
And streptococci, which form these long chains. It's almost like their microscopic ID badge.
That's a great visual for these tiny things. And then there's that other really crucial distinction that always comes up: gram-positive and gram-negative bacteria. This isn't just about some lab stain, is it? What's the real significance, practically speaking, for treatment?
Yeah, what's fascinating here is that the gram stain, it's not just a lab trick at all. It reveals a fundamental difference in their cell wall structure, and that directly dictates how we fight them.
How so?
Well, gram-positive bacteria, they have this thick peptidoglycan layer in their cell wall. But gram-negative bacteria have a thinner layer and, crucially, this extra outer membrane.
An outer membrane, like armor.
Exactly like armor. It acts like an extra shield for those gram-negative ones, often making them naturally more resistant to certain drugs. That's why, as our sources point out, gram-positive bacteria are typically more sensitive to many common antibiotic treatments. Understanding that structure really helps doctors pick the right weapon, It tells you what kind of armor the bacteria are wearing.
That makes perfect sense. And speaking of picking the right weapon, let's clear up some terms because they often get thrown around kind of interchangeably and it leads to confusion. We hear antiseptic, disinfectant, antimicrobial, antibiotic. Can you maybe define these precisely for us? What's the real nuance?
Absolutely. Yeah, the distinctions are important. Think of it this way: an antiseptic that's specifically designed for living tissue, like your skin, to inhibit infection. It's safe for the body.
Okay. Skin.
A disinfectant, though, that's much stronger.
Yeah.
It's for non-living objects, countertops, hospital surfaces, things like that. It's about sterilizing the environment.
Got it. Not for people.
Definitely not. Now, antimicrobial, that's the big umbrella term. It describes any agent that inhibits the growth of or kills bacteria and other microorganisms. That includes fungi, even viruses sometimes.
Okay. Broad category.
Very broad. And then specifically under that umbrella, you find antibiotics. Now, technically, these are derived from organic sources, often other microorganisms actually, and they specifically target bacteria, either inhibiting their growth or killing them outright.
So antibiotics are a specific type of antimicrobial really focused on bacteria. And even within antibiotics, you mentioned two major strategies: bacteriostatic versus bactericidal. How do those two approaches differ?
Yeah, it's a really crucial difference in strategy. Bacteriostatic drugs, they don't actually kill the bacteria directly. Instead, they inhibit their growth and reproduction.
So they just stop them.
Pretty much.
Yeah.
Think of it like putting the bacteria into suspended animation. It gives your body's immune system time to catch up and clear the infection itself. But bactericidal drugs, they're the direct assault force. They are designed to actively kill the bacteria. The choice between them: It really depends on the specific infection, the patient's immune strength, the type of bacteria. Lots of factors.
Right. Now, here's where it gets really interesting for me. How do they actually do that? How do these antibacterials wage war at the cellular level?
hmm
What are the specific mechanisms? This is where the cleverness comes in, isn't it?
It absolutely is. Our sources detail 5 main mechanisms, and understanding these really shows you how ingenious these compounds are at exploiting bacterial weaknesses. First, many work by inhibiting bacterial cell wall synthesis. Imagine trying to build a brick wall, but the mortar just won't set. The bacterial cell wall is vital for survival, so disrupting its formation basically stops the bacteria maintaining its structure or dividing.
Okay, attack the wall. Makes sense. What else?
Second, some alter the membrane permeability. This is like punching holes in their protective outer skin. Yeah, exactly. Their vital internal contents leak out and, well, that's the end of them. Third, a very common and effective strategy: inhibition of protein synthesis. Bacteria need proteins to function, grow, reproduce, just like us. These drugs essentially jam their protein-making factories.
Grind them to a halt.
Precisely. Then fourth, we have drugs that inhibit the synthesis of bacterial RNA and DNA. That's a direct hit on their genetic material. Stops them replicating or carrying out essential life processes.
Going right for the blueprint.
Exactly. And finally, number 5. Some antibacterials interfere with metabolism within the cell. They mess with energy production or other vital chemical reactions needed for survival. These different approaches. That's why different drugs target different bacteria so effectively. They exploit different vulnerabilities. Highly selective.
It's incredible. So many different fronts to attack. But hang on, before we even deploy these powerful drugs, our bodies have their own defenses, right? What are some of the key factors that contribute to our natural ability to fight off infections?
That's such a vital point and often gets overlooked. Your body's natural defenses are complex, incredibly effective. Our sources highlight several critical factors. Your age, for one, influences immune strength. Nutrition provides the essential building blocks.
Fuel for the fight.
Absolutely. Immunoglobulins, those are antibodies, basically the body's ID tags for pathogens. Efficient circulation is key, making sure immune cells get where they need to go quickly. Healthy white blood cells, WBCs, of course your primary infection fighters. And proper organ function. Many organs play roles in immunity, detox, waste removal. All these significantly influence your body's ability to fight things off, often before you even think about needing an antibacterial.
Which brings us nicely, or perhaps not so nicely, to one of the biggest challenges in modern medicine, something we hear about constantly: antibacterial resistance. This directly impacts every single person listening. Can you break down what resistance actually means and why it's such a huge global worry?
It's essentially an evolutionary arms race.
Yeah.
And yeah, it's a massive challenge.
Why?
Resistance happens when bacteria evolve ways to survive drugs designed to kill them. We usually distinguish between inherent resistance, where a type of bacteria is just naturally unaffected by a drug.
Like it was never going to work anyway.
Right. Maybe it lacks the target the drug aims for. But then there's acquired resistance. This is maybe more concerning. This is where bacteria, either through random genetic mutation or by picking up resistance genes from other bacteria, they develop resistance over time. And we're seeing the scary results, like the rise of healthcare-acquired infections, or HAIs, caused by these superbugs, things like MRSA.
Yeah, I've heard of MRSA.
Methicillin-resistant Staph aureus, or VREF, vancomycin-resistant Enterococcus faecium, and even VRSA, vancomycin-resistant Staph aureus. These are incredibly hard to treat because they've become resistant to many common antibiotics.
And our sources really hammered home that our misuse of antibiotics is a key driver here. What are the common ways we accidentally make this problem worse?
You're spot on. Our actions play a huge role. Resistance gets accelerated significantly when antibiotics are taken unnecessarily. Like when people take them for viruses, colds, the flu, where antibiotics do absolutely nothing.
Right, because it's a virus, not bacteria.
Exactly. Or when there's no bacterial infection actually present. Another major issue is taking antibiotics incorrectly. Skipping doses, not taking them at the right times, or maybe stopping the course early just because you feel better.
Oh, guilty. Sometimes you feel fine and just forget.
It's easily done, but every time we expose bacteria to a drug without completely wiping them out, we give the slightly tougher, more resistant ones a chance to survive, multiply, and pass on those resistance genes. It's natural selection and fast forward. And we also need to understand cross-resistance. This means if bacteria get resistant to one drug, they might also become resistant to other drugs with similar ways of working. That just shrinks our toolkit even further. It really raises an important question, for everyone listening. Are you always ensuring you take antibiotics exactly as prescribed, for the full duration, every single time. Your personal adherence is actually a critical part of this global fight.
That's a really powerful reminder. We all have a part to play. Now, sometimes doctors use different antibacterials together. What happens then when these drugs combine forces? And what about the downsides, adverse reactions?
Good question. When antibacterials are combined, the effects can vary quite a bit. You might get an additive effect where the combined impact is basically the sum of the two drugs, like 1 plus 1 equals 2, doubling the effect.
Okay, simple addition.
Then there's a potentiative effect. This is more interesting. One drug actually enhances the effect of the other, making the combo much stronger than just adding them up. 1 plus 1 equals 3 sort of thing.
More bang for your buck.
In a way, yes. But then there can also be an antagonistic effect. This can be a real problem, especially if you combine a bactericidal drug, one that kills, with a bacteriostatic one that just inhibits growth. They can actually work against each other.
How?
Well, the killing drug might need the bacteria to be actively growing or dividing to work properly. If the other drug stops them growing, you see the issue. The desired effect might be significantly reduced.
Okay, so combining isn't always better. What about those adverse reactions you mentioned?
Right, the downsides. Our sources highlight a few key categories. Probably the most serious is an allergic reaction. This can range from mild stuff, hypersensitivity, a rash, hives, all the way up to life-threatening anaphylactic shock. That needs immediate medical help.
Scary stuff.
It can be. Another big concern is superinfection. This happens when the antibacterial kills off not just the bad guys, but also the beneficial bacteria, the normal flora living in your body.
The good bacteria.
Exactly. And when they're gone, opportunistic pathogens, things that wouldn't normally cause trouble, can take over. This leads to a secondary infection. Common places for this are the mouth, skin, respiratory tract, GU tract, intestines, think thrush, or C. diff colitis.
Ah, right. I've heard of those.
And finally, there's always the risk of organ toxicity. Some antibacterials can be tough on certain organs, especially with high doses or long-term use. The sources specifically mention potential damage to the ear, liver, and kidney.
So clearly not a one-size-fits-all situation. Lots of potential risk, which I guess brings us to the idea of an antibacterial spectrum. They aren't all the same in what they target, are they? It's like precision versus broad attack.
That's an excellent analogy. We definitely distinguish between narrow spectrum and broad spectrum antibacterials.
Yeah.
Narrow spectrum drugs are like those precision guided missiles you mentioned. They're primarily effective against one specific type or a very limited range of bacteria. Classic examples are penicillin, which mostly hits gram-positive bacteria, and erythromycin. These are more like your carpet bombing analogy. Effective against a much wider range, both gram-positive and gram-negative bacteria. Think tetracycline or cephalosporins.
Okay, broad versus narrow. Why use broad if narrow is more targeted?
Well, if we connect this to the bigger picture, broad-spectrum drugs are frequently used to treat infections when the specific offending microorganism hasn't been identified yet by what's called a CNS, culture and sensitivity test. That's where doctors take a sample, blood, urine, sputum, whatever, grow the bacteria in the lab, and then test different antibiotics against it to see which one works best, kills it most effectively.
Okay. See what it's sensitive to.
Exactly. But that takes time, maybe 24, 48 hours, sometimes longer. Someone's really sick, you can't always wait. So you might start them on a broad-spectrum drug right away to cover the most likely culprits and get ahead of the infection. Then once the CNS results come back, you can switch to a more targeted, narrow-spectrum drug if appropriate.
That makes so much sense. Start broad, then narrow down when you know the target. Okay, to round things out, our sources also had a quick glossary of related terms. Good ones to have in your vocabulary when thinking about disease spread.
Absolutely. Quick definitions are useful. When something is infectious, it just means the pathogen, the bug, has found a way into the body and started to colonize.
Got in.
Right. If it's contagious, that specifically means it can be spread from person to person, like the flu.
Okay, person to person.
Virulent refers to how good a pathogen is at causing disease, how severe it makes you sick. A highly virulent bug causes serious illness.
Nasty factor.
Pretty much. A vector is a living organism that delivers a disease. Think mosquitoes carrying malaria or ticks carrying Lyme disease.
The delivery service.
Exactly. A reservoir is where a disease normally lives and thrives. Could be animals, could be the soil, could be water.
Its home base.
And finally, fomites. These are inanimate objects that can carry disease. Doorknobs, phones, keyboards, shared pens, countertops.
Oh, right. Things you touch.
Exactly. The unsung transporters of illness. Easy to forget about.
Wow, what a deep dive indeed. We've covered so much ground, navigated the invisible world of bacteria, understood our powerful antibacterial arsenal, the good and the bad, and really confronted this escalating challenge of resistance. It just reinforces how complex this all is and how critically important it is to understand these drugs, not just for doctors, but for all of us. Thank you for joining us on this exploration.
My pleasure. And remember, becoming more informed about these topics, it genuinely empowers you. You can make better health decisions, understand why certain treatments are chosen, and just critically evaluate all the health information that's thrown at you daily. Knowledge really is your best defense in this microscopic war.
Absolutely. So, as we wrap up, here's something to chew on. In this ongoing evolutionary race against increasingly resistant bacteria, what comes next? What innovative strategies, maybe beyond traditional antibiotics, might we need to truly win the future of fighting bacterial infections? It's a huge question. Challenges researchers, doctors, policymakers globally every single day, and it's one we really encourage you to keep exploring. Keep that curiosity alive, and we'll see you next time on The Deep Dive.